Hello students. So here we are going to see a very small concept, that is when three hinged arches, when they are at same level, and at such case what is the formula for normal thrust and radial shear at any section of that particular three hinged arch. Okay, so coming to this case where we can see a three hinged arch. Okay, we can see here a three hinged arch where hinge at A, support B, and internal hinge at support C. Okay, three hinge arch we can see here. Now at support A there are two reactions because it is hinge, so there is a horizontal support HA, then there is a vertical reaction VA. At support B there are two reactions HB and VB. Okay, and there are some loads acting. Okay, W1, W2, W3. Now, for this particular case, our aim is to find out at any section, okay, at any point in the arch D, what is the normal thrust, what is the radial shear at this point. Okay, so because of this loading, whatever loading is acting on this particular arch, it will create, at each and every point there will be some normal thrust and radial shear throughout the arch. So what is that at particular point D? That is what we are going to find out. I mean we will be arriving at one formula over here. Now for as you are aware from your second year onwards, that whenever we want to analyze any structure, there are basic few equations of equilibrium, okay, without which we cannot solve the problem. So for statically determinate structure, we have these three equations of equilibrium, that is summation of forces in x direction is equal to 0, summation of forces in y direction means all vertical forces, okay, they are 0, and then moments. Okay, so for this particular case, moment at A and B is 0. Why 0? Because it's a hinge support. Okay, and whenever hinges are there, they are not capable, they cannot take moment, so they are 0. And then there is one more extra case here which you have not seen when it was a simply supported beam, right? For a simply supported beam case, you might not have, yeah, you have not seen it in second year. So here moment at this internal hinge also 0, so we see this extra case over here. Now for this particular arch, we don't see any horizontal forces. Okay, we don't see any horizontal forces. In that way, these two supports will be, they will be at rest, they will be sleeping because they don't have any work, there is no horizontal force acting. But at the same time, because of these vertical forces, this arch is trying to expand, is trying to move like this. I mean, it's trying to, because of this load, it is trying to go outward. So to that, definitely these horizontal forces, they become active. Okay, and they stop that outward movement of the arch. Okay, so here they are active horizontal forces. So coming to any point. Okay, now for this case, as there are no horizontal forces acting, so for this particular case, our horizontal reaction, that is HA, becomes equal to HB. So we consider that both of them are at of same quantity. Now when we don't use the equation summation of forces in y direction is 0, so we are left to solve this problem, we are left with these three equations only, that is summation of forces in y direction is 0, then moment at A and B is equal to 0, and moment at C is equal to 0. Okay, now since load tend to spread the arch, yes, just now I said that it's trying to spread the arch outward side, so the horizontal thrust, it helps to keep it intact in the position. Okay, so that is the about horizontal forces. Now let us see what happens when we consider any section D. Okay, so for this particular case, consider a section at D. Now in this particular case, let V be the vertical shear, Q be the radial shear, and N be the normal thrust. So let's see this diagram. So coming to this particular point, okay, here at point D, at this particular point D, the right hand portion of the curve we are just ignoring. Just see the left portion. So we see that there is this load W1. W1 is also there, and we just see we will be arriving at the formulas. Okay, so for this particular point D here, at this particular arch, whatever loads are acting, it is creating a normal thrust. Okay, N shows which is along this line, okay, along the point of D, that is a normal thrust. Now there is this radial shear which is perpendicular to the normal thrust. Okay, so at any point, at any particular section, when there are normal forces, then there will be a translational forces. Okay, shear will be there, so we call it as radial shear. Okay, and there is, for this normal, there will be two components, one horizontal and then one vertical, and for radial shear also there will be two components, one normal, uh, uh, one horizontal and one vertical. Okay, and it is angle theta. So to calculate the components, we can just use it as a, this particular triangle. Just if you draw like this, we can form a triangle over here, and using tan theta, sin theta, cos theta, so using those formulas, we can arrive at this final equations. So here, uh, since load tend to spread the arch, the horizontal type equation is here. So here thrust is in inward direction. Now here in the diagram, it's already, I told you that V is a vertical shear, Q is a radial shear, and N is a normal thrust. So we arrive at this important formula. So what is the normal thrust? N is equal to, okay, what is total normal thrust? That is, then we will see is two components, that is vertical component and horizontal component as well. So vertical component here, so that will become, make it, it is vertical component. So if you consider the theta, so it will become sin theta, right? So that is V sin theta. And for the horizontal component, so if you consider this angle, like if you see this diagram, so for this particular diagram, okay, for this normal thrust N we consider, so this becomes theta, right? Sin theta. So sin theta will be equal to this side, right? So what we'll write, normal thrust for it, one vertical component and one horizontal component. So that is V sin theta plus H cos theta. And for radial shear, its components will be V cos theta minus H sin theta. Okay, V cos theta minus H sin theta. So these are the two important equations we are going to use to solve the problem. So at any point on the arch, wherever we want to find out what is the normal thrust and what is the radial shear at any point, so using these equations we can solve any problem. Hope this small concept is clear to you. Okay, thank you so much.